Our next speaker is going to be Mark Safman. He is a pioneer of Rydberg atom quantum computing. And actually, I only learned when I was looking at the bios that you are also the Johannes Rydberg Chair of in physics of the Johannes Rydberg Professor at the University of Wisconsin, which is, I assume, not a coincidence. It's very interesting. He's also the director of the Wisconsin Quantum Institute, the chief scientist for quantum information at Inflection. He's been an associate editor of Physical Review A and has many awards, such as being a fellow of the Optical Society of America. So go ahead, and we're looking forward to your talk, Mark.
Great. So let me start by just saying thank you to Olga and the organizers for inviting me to speak to you here today. It's really stimulating to see the level of interest in growing what's already very strong quantum research in Texas, but also growing a quantum industry. Now, this is somewhat of a blended audience. We have some true world leaders, experts in quantum science and technology, and I'll also venture that some of you never took or suffered through a course on physics in your education. So I'll try and strike a middle ground and not get too deep into the technical details, but give you some flavor of what's going on and the advancements that are occurring with this neutral atom approach to quantum computing. And I'll just also add, I got here a little late because of some flight delays. I did not hear Mikhail Lukin's talk this morning. There may well be some overlap, but since I didn't hear it, I'm not going to worry about that. So here's a picture of an atom array, and I'm working on these things at the university and at Inflection. And just taking a step back to start, there are a number of different platforms that you can think about using for developing quantum computers. There's these 5 leading modalities shown on the top there: trapped ions, optical, superconductors, quantum dots, neutral atoms. There's even a few more outliers, and there's a couple of things to say about them. These are very different physical approaches. The microscopic physics of how they work, why they're good for or not for quantum computing, is very different. Each modality has strengths and challenges, but I would emphasize that the end game is not necessarily winner takes all. It may well be a combination of solutions using these different platforms. So let me give you a sense of how we build up these neutral atom arrays. And it really starts with a small vacuum cell, sort of centimeter size, that you could fit in the palm of your hand. There's actually a whole lot of other equipment that goes around it, lasers and electronics and so on. But the core of it is this very small centimeter scale glass cell, and this is one of these advanced cells that Inflection has developed. And then we shine laser beams at that cell, and we create a small cloud of very cold atoms. And this technique of laser cooling is now 35, 40 years old, and it's become one of the standard pieces in the toolbox of practicing atomic physicists, and it's really not difficult. We have these kind of laser cooling experiments in our undergraduate labs at the university. I'd venture there may well be some high schools around that actually have a laser cooling experiment in one of their high school classes. But with very straightforward techniques, we shine laser beams at that cell, and we have this cloud of 1 million cold atoms. So that's our qubit fab. We don't have to go out and do difficult lithography. We have those atoms right there, and then we can work with them. And the next step is we shine some patterned light on top of that cloud, and we prepare these arrays of individual atoms. And what you're seeing is a fluorescence image of the light scattered from individual atoms laid out in this regular array. Now, I'm sweeping under the rug a couple little details. When you go from the disordered cloud to the array, some of the sites are empty, so you have to take a picture, see which ones are empty, and then move the atoms around to fill up the region you want to work with, but people know how to do that now, and so you can very directly generate these very beautiful arrays of individual atoms. And that's become a very active research area, in part because it's not so hard to get started, and the technical tools you need are not that hard. I have here a $10 laser pointer with a little optic on the front of it, and it creates a pattern of light beams. And you can trap individual atoms essentially in those light beams using relatively simple optics. And you can do that with different species, with different geometries. You can even do it in 3D and make an atomic Eiffel Tower, as Antoine Brouet did in Paris some years ago, which is really quite amazing, I think. But this is the starting point for working with these neutral atom qubits. So having one of these arrays, how do we go from there to a quantum computer? And it depends, the details depend on which atomic element you choose to use. I'm going to describe it in terms of cesium, which we use in some of my labs. And if you look at the lowest levels of cesium, there's these two levels that are separated by 9.2 gigahertz. We like to describe energies in terms of frequencies as physicists. And that's exactly the energy separation, which currently is the international definition of time. So I like to call this an SI, or industry standard qubit, that we're working with when we use cesium atoms. So we can encode our qubits in those levels. And if we want to change the superposition, move population around between those levels, we turn on some resonant microwave, illuminate this array with a horn, and we can change the population between the two levels. To access arbitrary quantum states, we also need to control phases between those levels, and we do that with a laser beam. We focus individual spots to single atoms, and that imparts a phase to one of these levels, and the combination of the microwaves and the laser beam gives us full control of preparing arbitrary quantum states. We then add one more laser beam that goes up to these Rydberg states that Caden mentioned. And then if we excite two atoms next to each other to these Rydberg states, they have this enormous interaction that, depending exactly which level we go to, how close the atoms are to each other, it can range from 10 megahertz to 100 or possibly even a gigahertz. So you have this enormous interaction, which you can turn on and off with laser pulses, and that interaction entangles pairs of atoms and provides the basis for performing quantum logic and computation. So in a nutshell, these are sort of the tools we use. And then in the last few years, using those tools, there's been a great progress in showing we could implement quantum circuits and run algorithms on these emerging quantum computers. And we did this running some small algorithms in Madison a couple years ago. A very powerful paradigm for the quantum computer, which Mikhail would have talked about this morning, is this notion of using transport, not just to put atoms where we're missing them, but to use transport of atoms within a quantum computation to enable connectivity, and to use this zoned architecture where you have a region where you have memory or storage, you have a region where you're performing logic and entanglement, and another region where you're measuring the results. And so different combinations of these approaches have now been demonstrated by a number of players, including a bunch of companies. And I think in the near future, we'll see many more groups also demonstrating quantum circuit, quantum applications with this neutral atom approach. Let me go into a little bit more detail about what we're doing in Madison and at Inflection. So we, some years ago, demonstrated some small algorithms, made entangled states, the phase estimation algorithm, something called quantum approximate optimization algorithm, using this focus beams pointing to different atoms. We then showed that by being very careful about the optical engineering, paying good attention to having pristine beam quality, very stable optical trains, and so on, we could achieve essentially the same performance, the same entanglement fidelity with these very small focus beams as you can with the large beams in the zoned architecture. And then we showed we could also change the geometry, the connectivity, by going from this square lattice to a triangular lattice, and implemented last year some logical qubits and benchmarked them for a material science application. And then earlier this year, we started combining this notion of focus beams with transport within the circuit, where we both move atoms around and move the laser beams around. This was for a demonstration of a variational quantum eigensolver analyzing a spin model from quantum physics. And so I want to show you now just the latest result from Inflection. This went up on the archive earlier this week, where we've now extended this approach of combining focus beams that we can rapidly scan using optical pointing devices with atom transport to give us an alternative architecture for implementing logical qubits. And so instead of having zones, what we're doing here is purposefully leaving some of the sites empty and then moving atoms from sites where they were into these empty sites, and then doing the gate operations and also measurements in place. And then the transport here is providing the logical connectivity, but not requiring that we always move over to some other zoned location. So using this architecture, we can have all-to-all connectivity using motion, but we're going to use motion sparingly. The downside of motion is that you get some heating of the atoms, some loss of the atoms, and so in a long circuit, you will have to get rid of that extra heat and do some recooling. We've been running logical circuits with about 100 qubits in a roughly 200-site array. We've been able to show that we can have entangling fidelity of about 99.7. This is a post-selected number. And the next step will be to show that we can actually do in-place crosstalk-free measurements. One of the approaches to that is using 2 atomic species in one array. So with this architecture, we demonstrated 3 primitives. One was a demonstration of Shor's algorithm for factoring using logical qubits, something called a C-naught ladder, and a larger error-correcting code of many hypercube code. And I'll go through these and show you what we did. But what I'm plotting here is something called total variation distance, which is essentially the error in the results of the circuit. Lower is better. And what you're seeing is that for each of these 3 primitives, the error, post-selected error using logical qubits is substantially lower than the error in these gray bars of the unencoded physical level circuit. So the Shor's algorithm, Shor is sort of the quantum algorithm that kickstarted the enormous interest and investment in the field. Logical qubits will, of course, be needed for future cryptographically relevant use cases that are going to need 1 million or so qubits to go beyond classical. What we've done is the first demonstration using logical as opposed to physically encoded qubits. This was done with a small code. So this notation here, 422, means we're using 4 physical qubits to encode 2 logical qubits at distance 2. And the distance number is a proxy for how effective the code is at detecting and correcting errors. When the distance is only 2, it's not an error-correcting code, but it tells you if an error occurred, and so you can choose to ignore those cases where you had an error and just look at the error-free results. And so we ran Shor for different cases. Again, this is the total variation distance. This is the unencoded result, and different versions of the logically encoded circuit gave substantially lower error. Something else we did was something we call a constant depth C-naught ladder. This was with 12 logical qubits. This type of circuit where you have a string of C-naught gates after each other is a way of creating large maximally entangled states. And if you combine this with mid-circuit measurements, you can create GHC, entangled states. And so we showed that we could convert this type of circuit that has a depth that scales with the number of qubits we're entangling into a constant depth or single time cycle circuit. And again, comparing unencoded in gray with encoded in green, we could get substantially better performance. And then finally, we demonstrated preparation of a logical state in something called a many hypercube quantum error correcting code. What we're doing here is taking that 422 code, and each one of these 4 physical qubits is itself encoded in another 4 qubits, which gives us 1644. This is now an error correcting code with distance 4. And this comes from this paper from Goto. And again, we showed that the encoded results were better than unencoded. So what are the aspirations for the next few years? We just heard from Worley, we should be serious and stop saying we're going to do something until we do it, perhaps. But we do need to talk to people about what we're planning and what we expect is possible. The community as such would like to see things like entry-level quantum chemistry applications. In round numbers, we could hope for 100 logical qubits with 1 mega QOP or 1 million operation deep circuits being run on those 100 qubits. I don't want to give you a even power of 10 as for the timeline in years as to when that's going to happen. I think it can be shorter than that, but we'll see. But even beyond that, it's pretty clear that to really access the full range of really valuable applications of quantum computers, working together, of course, with classical computers, we're going to have to look at larger systems with more qubits and deeper circuits. The DARPA QBI program identified a range of applications with growing system size, growing computational depth, and growing numbers of physical qubits. And so you can ask the question, how do we get from today's circuits with order a few hundred qubits on neutral atom platforms, on superconducting platforms, to larger systems with 100,000, a million, 10 million, or perhaps even more qubits? So let me show you a couple slides saying a few things about neutral atom challenges to get there. One thing to say is that improving the gate fidelity can reduce qubit requirements by an order of magnitude or more. Here's a plot of the neutral atom entangling gate fidelity since the first experiments in 2010 up until recent results. Lower is better in this plot. And for 4 different atomic species, we now see results clustered here pushing towards 3/9 of fidelity. It's, I would say, reassuring to know as an atomic physicist that really the fundamental physical limits on Rydberg gate fidelity are about 5/9. And if you give me another half hour, I can tell you why that is. But this gap here is primarily technical and requires better lasers and optics. So I'm going to say I think there's a real path towards getting to those 5/9 with these atomic systems. And we're able to say that because atoms are relatively simple. We understand them with great precision. We can write down formulas that describe their behavior with great accuracy, and that supports these kind of statements. How big can we make one qubit array? Can we get to that million or 10 million qubits in one array? And there has indeed been great progress in recent years in the array sizes that has been demonstrated, up to more than 10,000 in a work last year from Caltech. The optical power per trapped atom is at least about a milliwatt, it turns out. And so 100,000 atoms is 100 watts. A million would be 1,000 watts. You can buy a laser that big, but it's hard to do precision work when you have that much laser light flying around. And then we also have to think about mundane things like light being absorbed in glass walls and so on. And so that suggests that, we can't just scale this up to arbitrarily large numbers, and it suggests that we think about modular architectures. And so that's something we've also been working on a lot. In the Midwest, we have a Quantum Leap Challenge Institute supported by the NSF called HCAN for Hybrid Quantum Architectures and Networks. And there's a number of groups within that center working on different ways of building something like this, connecting multiple quantum processor nodes in a larger modular system. And in my lab, we've been working on doing this with optics, having arrays of atoms coupling to photons, measuring the photons, and by entanglement swapping, preparing the atoms in entangled states. And so let me show you in just slightly more detail how this works. I have an atom here that I can collect photons from. If I excite that atom to an excited state, it will decay down, emitting a photon. And depending on the polarization of the photon that's emitted, I end up in this atomic state or that atomic state. And the net result is I create an entangled state of the atom and the polarization state of the photon. And so we've built 2 nodes, Alice and Bob. This is the apparatus that has that inside of it. And this is the distribution of the photon that comes out. And we can do correlation measurements and verify we have very pure single photons, and then work to entangle them on these beam splitters. We're not quite there yet, but we have good preliminary data showing that we are preparing atom-photon entanglement with close to 95% fidelity. And the next step is to do this from both simultaneously and entangle atoms here and atoms there as a step towards a modular processor. Now, I started at the beginning saying that there's many modalities that you can do quantum computing with. And one of the features, though, that I want to emphasize of atoms is that they can do more than computing. If we have this kind of connected network, we can think about using it not just for computing, but for distributed sensing and secure communications. And so one of the great features of atoms, which really Inflection is leveraging, is that we're not just working on computing. We have an optical atomic clock product, and we have a lot of efforts underway for quantum sensing, both sensing electromagnetic fields, but also inertial and gravitational sensing using atomic sensors. And so I'll just end here and point out that neutral atoms are scaling very fast, I think faster than any other modality, and I think the next couple of years are going to be interesting. Thank you.
So maybe we can have one quick question while Mukund comes up and gets ready. Anyone have a very quick question?
Ratio of logical to physical qubits.
It depends on the code distance you want to use. We had a ratio of 2 to 1, distance 2 code. These many hypercube codes are a ratio of about 4 to 1.
All right, let's thank Mark again.